Hi, I'm Melanie.
And my name is Bob. We'd like to talk to you about reactions, but more specifically about the reactions of ions in aqueous solutions. The type that we want to focus on here are double replacement reactions. Solving problems with this type of reaction can sometimes seem difficult and maybe even a little intimidating. But we will present a four-step process that should help you working with these problems and show you how to predict the products of these reactions. Let's go to the classroom and I will describe the process. A common type of double replacement reaction is called a precipitation reaction. In a precipitation reaction, two compounds in an aqueous solution appear to exchange ions. Let me show you the general form of a precipitation reaction. Here we have a compound with cation A and anion X reacting with a compound with cation B and anion Y, which yields a compound with cation A and anion Y, and a compound with cation B and anion X. In a precipitation reaction, at least one of the new product pairs formed will be a solid precipitate. We want to illustrate the process for predicting the products of a precipitation reaction. It involves four steps. For the best results, these steps should be performed in order. When you do this, you'll be able to predict if a reaction actually happened. You'll also be able to write a balanced equation for the reaction. And finally, you'll be able to tell what solid was formed, if any. Now, I will show you a specific example and guide you through these four steps. Suppose your professor asks you to predict the products of a reaction involving mercury 2 nitrate and potassium iodide. What we would do first is refer to the periodic table. Here we find mercury, symbol Hg. Nitrate I will discuss in a moment as it is a polyatomic ion. We also have potassium, and note its position in group 1 column, indicating it carries a 1+ charge, and iodine. And note its position here in column 7, indicating that it carries a 1- charge. With respect to the nitrate ion, we refer to the polyatomic ion table. I reproduce that here. This is a table that is provided to us by our professor for use on examinations and to finish homework. We see here the table of ions and charges in polyatomic ions of various ions and the particular charges that they carry. In the box showing a 1- charge, we see nitrate, NO3. Now we've accounted for the charges on all of the ions in this particular reaction. In step 1 of this process, we will exchange the ions. We exchange the mercury cation with the iodide anion and the potassium cation with the nitrate anion. Because nitrate is a polyatomic ion, we treat it as the anion here. I've reproduced here the initial reactants. We're now going to exchange the ions. However, since we've accounted for the charges in the reactants, let's go ahead and add those in. With mercury, so it's a 2+ charge, the nitrate ion, a 1- charge, the potassium cation, a 1+ charge, and the iodide anion, a 1- charge. We'll now exchange the cations and anions. We'll start with mercury. The cation we will exchange with the iodide anion. Go ahead and add the charges. And we will take the potassium cation and exchange it with the nitrate anion. That's what is performed in step 1, simply an exchange of the ions. In step 2 of the process, we balance the charges of the reactants and products to get the correct formula. We can use the crisscross method. we have to balance the charges knowing that each compound must result in a neutral charge. We've shown the charges again, the mercury with 2+, nitrate ion with 1-, potassium with 1+, iodide with 1-. In exchanging the ions from step 1, we've assigned the charges in a similar fashion. Now, using a crisscross method, we can add boxes in here to do that crisscross. Find that helpful in keeping track of the charges and balancing them. Here, in order to get a neutral charge and balance where we have 2+ with mercury, doing crisscross here to here, we find that 2 nitrate ions would give a 2- charge, balancing with the 1 mercury atom with the 2+ charge. When we find that we have a single atom, we don't actually show the 1. We leave that off. In the case of the nitrate ion, where there's 2, and it's a polyatomic ion, we place that in parentheses and show the 2 as a subscript. That eliminates any confusion with respect to a reader interpreting without the parentheses, a 2 after the 3 is that meaning oxygen 32 atoms, which would be incorrect. Moving on to potassium iodide, crisscross 1 and 1, no change there. Both is simply 1. On the product side, again, to balance here, would require 2 atoms of iodine with a 1- charge to create a neutral charge with the mercury. So we simply take off the 1, put the 2, and we find that with 1+ and 1-, the potassium nitrate is in balance. So we can simply leave that as 1 and 1. We have now balanced the charges in step 2 and expressed a correct formula. In step 3, we balanced the equation that was the result of step 2. I've recopied that here. It's handy when doing this is to set up a table to keep track of the count of the ions on both sides of the equation. So I will add a mercury, a nitrate, a potassium, and an iodine. And we'll simply count those atoms or ions on each side of the equation. On the reactant side, mercury, there's 1. On the product side, also 1. With respect to nitrate, on the reactant side, we have 2 ions. On the product side, 1. With respect to potassium, reactant side 1, and also 1 on the product side. And with iodine, we have 1 on the reactant side and 2 on the product side. When balancing now, we can use these numbers from this table. With mercury, we have 1 on both sides, so we're in balance there. With respect to nitrate, we show that we have 2 on the reactant side and only 1 on the product side. So, in viewing this, in order to correct that, we can make this a coefficient of 2 in order to get 2 nitrates. However, when we do that, we can change that to 2, but we also have to correct that we have 2 potassium on the product side also. So we make that 2. Going to potassium next, we find that we have nitrate in balance now. Going to potassium next, we show 2, of course, on the product side and 1 on the reactant side. So to bring that into balance, we can make that a coefficient of 2. In doing that, we recalculate our count. Now potassium on the reactant side is 2, but we also have to make that same change with respect to the iodine, changing that on the reactant side to 2 also. Now checking potassium, we find we have 2 on both sides of the equation, and we also have 2 iodine. Consequently, this is in balance. This is our balanced equation. In step 4, we check to see if each of the products is soluble in water. For this, we will use the solubility rules table that was given to us in our class notes. However, if you don't have this, you can look up solubility information from a variety of references and sources, such as online on Google. I'm going to show you the solubility table, a reproduction of that, from our class notes. The way we use this is to first look at the anion in the products. In this case, we're going to have a nitrate anion and also an iodide anion. We'll pan back over here and look at the actual equation left from step 3. With respect to the mercury iodide, we want to see if that is soluble in water. So again, using the anion iodide, we see under the compound column iodides, and that is shown to be water soluble. In other words, we would expect that to be aqueous. However, we want to look for any known exceptions to that rule. With respect to the iodides, exceptions would be compounds containing silver, lead, or mercury. Well, in this case, it is coupled with mercury, so it is an exception. So that would be water insoluble. In other words, it would form a solid or a precipitate. So to express the state, we simply put in parentheses after the compound an S for solid. With respect to the potassium nitrate, we look at the nitrate anion on the chart, and we see under the compound column nitrates, and they are expected to be water soluble or aqueous. Any exceptions to that? It shows none. So in all cases, if a nitrate anion appears, it would be an aqueous solution. So we go back to our equation, and in parentheses for state, we put aqueous, and we've determined the solubility of our products. The mercury iodide is a solid precipitate, and the potassium nitrate is an aqueous solution. If one or more of the products in this reaction are an insoluble solid, then a chemical reaction has occurred. The formation of a solid precipitate is evidence of that. If both products are soluble or aqueous, then this is only a physical change. No chemical change has occurred. So if asked, in that case, you would simply say that there has been no reaction. However, here, with the presence of a solid precipitate, that is evidence of chemical reaction. This four-step process allows us to systematically and reliably predict if a reaction has occurred. It gives us a correct balanced equation, and it tells us what solid precipitates are formed, if any. To confirm that this process works using this example, we will go into the laboratory and test it. So let's take a little closer look.
We are now in the lab to test and see if our prediction is correct. I have already measured 2 milliliters of potassium iodide and mercury 2 nitrate. We're going to mix them together to see what happens. As we can see, a solid precipitate has formed. This is clear evidence that a reaction has occurred. Our prediction was verified.
We hope this video has helped you to solve problems with double replacement reactions.
Maybe this will help make your life a little bit easier in chemistry.